The current view is that the universe began with what's called the Big Bang. Immediately following that was a stage of inflation, an exponential expansion. For those who think 93 billion light-years across is massive, well, that's just the part of the universe we can see. There's potentially an infinite amount more stretching beyond what we can currently observe. It's a mystery, but guess what? We've got the James Webb Space Telescope to help uncover these cosmic secrets. Combined with the brainpower of thinkers like Roger Penrose, we're pushing the boundaries of what we know about our incredible universe. Let's dive in. The observable universe is pretty massive, and when we try to get a handle on its size, we usually talk about what's called the observable universe. So, what's that, you ask? Well, it's basically the part of the universe that we can see from here on Earth. Think of it like this: light travels super fast, right? Like, the fastest thing we know of. But even with that speed, light takes time to get from one place to another. Now, the universe is around 13.8 billion years old, so when we look at something really far away, we're actually seeing the light that left that thing a long time ago. If something is so far away that its light would have taken more than 13.8 billion years to reach us, well, we just can't see it because the universe hasn't been around long enough for that light to get to us. So, our observable universe is like a big bubble around us, going out as far as light could have traveled since the universe started. Turns out that's about 46 billion light-years in any direction from us. Why is it bigger than 13.8 billion light-years if the universe is only 13.8 billion years old? How can it be that big? Well, it's because the universe has been expanding since the beginning, so things that emitted light 13.8 billion years ago are now further away. Okay, so that gives us a bubble or a sphere around us that's 93 billion light-years across. Huge, right? And that's just the part of the universe we can see. There could be way more universe out there that we just can't see yet because the light hasn't had time to get to us. Now, within our big old observable universe bubble, there's loads going on. There are at least 2 trillion galaxies, and each one of those is home to billions or even trillions of stars, plus planets and other objects. And it's not just about the things we can see, like stars and galaxies. There's a whole lot of stuff in the universe that we can't see directly, but we know it's there. Stuff like dark matter, which is this mysterious substance that we can't see or touch, but we know it's there because of the way galaxies move. And then there's dark energy, which is even weirder, and it's what's causing the universe to expand faster and faster. Then there's also this faint glow of radiation all throughout space called the cosmic microwave background. It's like the afterglow from the Big Bang, the event that started the universe. And there are also things called neutrinos whizzing around, tiny particles that barely interact with anything, but we know they're there. Since we can't pick up any signals from beyond our observable patch, we really don't know what's out there. One of the strangest things about our universe is that it's not standing still. It's like it's on a constant growth spurt, always stretching and expanding. This means everything in it, from galaxies to clusters of galaxies, is getting further and further apart. Some things that we can see now will eventually drift so far away that they'll disappear from our view. This expanding universe also messes with the signals we get from faraway sources. It stretches out the waves of light, making them longer. We call this redshift. The further away something is, the more its light is redshifted. The universe is like a grand cosmic show, and we've got front row seats. But here's the catch: we're watching everything on a delay. You look at a star 10 light-years away, and you're not seeing it as it is now, you're seeing the light that left it 10 years ago. So, you're seeing the star as it was back then. The further away an object is, the older the light we're seeing from it. So, we can see way back in time, almost to the beginning of the universe, just by looking further out. That means by checking out objects at different distances, we can basically map out the entire history and evolution of the universe, right from the get-go to today. Now, the sun and the moon may look close, but they're actually pretty far from us. Starting with the sun, it's a whopping 150 million kilometers away from us, give or take. That's around 93 million miles. We call this distance 1 astronomical unit, or AU for short. But it's not always the same because Earth doesn't orbit the sun in a perfect circle, it's more of an ellipse or a slightly stretched out circle. So, when Earth is closest to the sun, which usually happens in early January, we're about 147 million kilometers or 91 million miles away. We call this perihelion. On the flip side, when we're at our farthest point from the Sun, usually in early July, we're about 152 million kilometers or 94 million miles away. This is called aphelion. Now let's talk about our Moon. The average distance between Earth and the Moon is about 384,000 kilometers or 238,000 miles. That's 26 cents. Like the Sun, the Moon's distance isn't always the same because it also orbits Earth in an ellipse. Once a month, the Moon gets closest to us at about 363,000 kilometers or 225,000 miles. This is known as perigee. And about once a month, it's at its farthest point, around 405,000 kilometers or 251,000 miles away, which we call apogee. To put these massive distances into perspective, let's say hypothetically you could travel at the speed of light. It would take you around 8 minutes to reach the Sun from Earth. For the Moon, it's a super quick 1.3-second journey. But what if you could only travel at the speed of sound? Well, that journey to the Sun would take you about 14 years, and for the Moon, you'd be looking at around 10 days. We all know our nearest stellar neighbor is the Sun, relatively speaking, but what about the second closest? That would be Proxima Centauri, and it's part of a fascinating three-star system named Alpha Centauri. Proxima Centauri isn't like our Sun, though. It's a red dwarf star, a bit more modest and chill, you could say. But when it comes to distance, it's about 4.25 light-years away from us here on Earth. Now, when we talk about a light-year, we're talking about how far light travels in a year. So, when we see Proxima Centauri from our telescope, we see it as it was 4.25 years ago. There's also something super interesting about Proxima Centauri. It's got planets, at least 2 that we know of, and one of them might just be in the habitable zone. That's the sweet spot where conditions could allow liquid water to exist on a planet's surface. It's the Goldilocks zone, not too hot, not too cold, but just right. It gives us a sliver of hope that maybe, just maybe, we might find life out there. But let's not forget about the other 2 stars in the Alpha Centauri system, Alpha Centauri A and Alpha Centauri B. They're more like our Sun in size and brightness. These 2 celestial buddies orbit each other, and they're around 23 times the distance from the Earth to the Sun away from each other. From Earth, they're a bit farther than Proxima Centauri, around 4.37 light-years away. So, how far is this really? Well, let's think about it in terms of travel time. If we could move at the speed of light, we could get to Proxima Centauri in 4.25 years. But what if we could only travel at the speed of sound? Well, you'd better be prepared for a long trip, like, very long. We're talking about 77,000 years to get to Proxima Centauri. Zooming out, let's look at the distance and size of the Milky Way. Did you know we've never seen a real photo of the full Milky Way? What we see are artists' impressions, best guesses, or photos of other galaxies that we think look like ours. Here's why: our galaxy is massive, about 100,000 light-years across. A light-year is the distance light travels in a year, which is crazy far, around 9.5 trillion kilometers. So, to take a selfie of our galaxy, we'd have to send a camera so far away that it would take more time than the universe has been around just to get into position, and then we'd have to wait millennia more for the photo to make its way back to us. Think about it this way: since we invented the radio in the early 1900s, its signals have been spreading out into the universe. But even traveling at the speed of light, they've only had about 100 years to travel, so they're only about 100 light-years away. Considering our galaxy is 100,000 light-years across, that's not far at all. So, 99.99% of the stars in our galaxy haven't heard from us yet. But even though the Milky Way is huge, we can only see a tiny part of it from Earth. On a clear night, far from city lights, you might see about 3,000 stars with your bare eyes. Now, let's talk more about the Milky Way. It's like a big, flat disk between 100,000 and 200,000 light-years across and up to tens of thousands of light-years thick, especially towards the center. Speaking of the center, there's a bulge there, a roundish blob about 12,000 light-years across. Our Sun is located about 26,000 light-years away from the center, in a part of the galaxy we call the Orion Arm. Our Milky Way is chock full of stars, somewhere between 100 and 400 billion of them, and there are at least as many planets. At the center of it all is an incredibly strong radio source known as Sagittarius A*, which we think is a supermassive black hole with a mass of 4.1 million suns. As for other galaxies, they're not exactly next-door neighbors. The closest major galaxy to ours is the Andromeda Galaxy, and it's a whopping 2.5 million light-years away. Other galaxies in our local group range from about 25,000 to 4.5 million light-years away. Speaking of the local group, turns out that our galaxy, the Milky Way, is not hanging out solo. We've got company. Over 20 other galaxies are part of our local group. The local group stretches about 10 million light-years across, so it's no small suburb. Altogether, all the stars in the local group galaxies add up to a whopping 2 trillion times the mass of our Sun. Credit for realizing the local group exists goes to Edwin Hubble. He's the guy they named the Hubble Space Telescope after. Back in the day, when scientists were just figuring out how far away and fast everything in space was moving, Hubble made a crucial discovery. He realized some of the stuff we thought was part of the Milky Way was actually way farther away. They were other galaxies, like Andromeda and Triangulum. Not only did Hubble figure out they were separate galaxies, but he also found that they were moving toward each other, like they were being pulled by some sort of invisible cosmic magnet. Turns out that the invisible magnet was gravity. So, what does the local group look like? Well, on one end, you've got the Milky Way and its bunch of satellite galaxies. On the other end, there's the Andromeda Galaxy with its collection of satellites. The distance between these two ends is about 3 million light-years, and they're heading toward each other at a speed of 123 kilometers per second. Both the Milky Way and Andromeda are spiral galaxies, and they are the big shots in the local group, each one containing around 1 trillion times the mass of our Sun. They each have their group of mostly dwarf galaxies tagging along. After our Milky Way and Andromeda, the next heavyweight in our local group is the Triangulum Galaxy, or M33 as some people call it. This is another spiral galaxy, but it's a bit smaller, with a mass of around 50 billion times that of our Sun. There's a bit of a question mark around Triangulum's relationship with Andromeda. They're not far from each other in cosmic terms, just 750,000 light-years apart. About 2 to 4 billion years ago, they had a close encounter that sparked a lot of starbirth in Andromeda. But whether Triangulum is Andromeda's sidekick or just a passing acquaintance is still up for debate. So, we've talked about our home galaxy, the Milky Way, and its neighbors in our local group. Now, let's take a few steps back and look at the bigger picture of our neighborhood in the wider universe, the Virgo Supercluster. Think of the Virgo Supercluster as a bustling metropolis of galaxies. It's not just our local group hanging out there, but over 100 other galaxy groups and clusters. In terms of size, it's mind-blowingly huge, about 110 million light-years across, and it's heavy too, with a mass of around 1,480 trillion times the mass of our Sun. But the Virgo Supercluster isn't some lonely island in the cosmos, it's one of many superclusters that make up the observable universe. It's also part of a larger structure called the Pisces-Cetus Supercluster complex, a sort of gigantic thread of galaxies stretched out across the universe. The person who first figured out the Virgo Supercluster was a thing is Gerard de Vaucouleurs. Back in the 1950s, he realized there was this big group of galaxies that included our local group. He called it the local supergalaxy and later the local supercluster. To figure this out, de Vaucouleurs built on the work of Edwin Hubble. Hubble also figured out that they were heading towards each other because of gravity. De Vaucouleurs took these findings and used them to identify the Virgo Supercluster. So, when we talk about our place in the universe, it's not just about our planet or our galaxy. We're part of the local group, which is part of the Virgo Supercluster, which is part of the Pisces-Cetus Supercluster complex, which is part of the whole vast universe. And that universe is full of other planets, galaxies, groups, clusters, superclusters, and complexes. We have established that the Virgo Supercluster is this big collection of galaxies, but it's not just a random jumble of galaxies. It's got some structure to it. In the middle, you've got this flat disk where most of the bright, shiny galaxies are. It's kinda stretched out along this thing called the supergalactic plane. This plane isn't a physical thing, it's an imaginary line that astronomers use to map out where the galaxies in the supercluster are. Then around it is the halo of the supercluster, and it's more or less spherical. It contains all the other galaxies that aren't in the disk. At the heart of the supercluster, close to the center of that disk, is the Virgo cluster. This cluster is the biggest and heaviest member of the supercluster, weighing in at around 1 quadrillion times the mass of our Sun and home to over 1,300 galaxies. Our local group is like a house on the outskirts of this galactic city, located on a small string of galaxies that stretches from the Fornax cluster to the Virgo cluster. So why is the Virgo supercluster such a big deal for astronomers? Well, it gives them a window into a bunch of different things. They can use it to study how galaxies come into being, change over time, interact with each other, and are shaped by their surroundings. The supercluster also offers hints about the wider structure of the universe, how it's expanding, and the mysterious stuff we call dark matter and dark energy. In fact, astronomers have noticed that the Virgo supercluster is slowly moving towards an area of space called the Great Attractor. This is a spot where gravity seems to be way stronger than normal, and it's pulling in the Virgo supercluster and a bunch of other nearby superclusters. On top of all that, a study in 2014 suggested that the Virgo supercluster isn't a standalone structure. Instead, it's part of a bigger supercluster called Laniakea. That's a Hawaiian word, and it translates to immense heaven. Laniakea Supercluster is the home turf of our Milky Way and about 100,000 other nearby galaxies. To give you an idea of the scale, Laniakea stretches about 520 million light-years across. In terms of mass, it's a mind-boggling 100 quadrillion times the mass of our Sun. Just like the Virgo Supercluster, Laniakea is part of a bigger structure known as the Pisces-Cetus Supercluster complex. This is a massive thread of galaxies that weaves through the universe. But Laniakea is just one of many superclusters in the universe that we can see. The Laniakea Supercluster is actually a pretty recent addition to our cosmic map. In September 2014, a team of astronomers came up with a new way to define superclusters. They did this by looking at how galaxies move relative to each other. The key to this approach was something called peculiar motion. It's a measure of a galaxy's total movement but with the part caused by the universe's expansion taken out. From there, the astronomers could map out the paths galaxies are taking, their flow lines, and figure out where the gravitational center pulling them in is. These gravitational centers are like the engines that drive superclusters. They pull galaxies towards them, shaping the structure of the supercluster. So, by mapping these flow lines and gravitational centers, astronomers were able to define the Laniakea supercluster and figure out its borders. Now, let's zoom in a little on Laniakea. This supercluster isn't one big homogeneous block. It's actually made up of 4 smaller parts. These used to be known as their own separate superclusters: Virgo, Hygrocentaurus, Pavewindus, and Southern Supercluster. So, where's the heart of Laniakea? It's right near this thing called the Great Attractor. That's a place in space that has a really strong gravitational pull, so strong that it's dragging in lots of nearby superclusters. It's a bit like a cosmic whirlpool, drawing everything around it in. Our local group, where the Milky Way hangs out, isn't right in the center of this action. We're more on the fringes of Laniakea, in a thin line of galaxies that goes from the Fornax cluster to the Virgo supercluster. And like the Virgo supercluster, Laniakea gives astronomers some important clues about the bigger picture of the universe, including its structure and how it's expanding. It can also help them learn more about dark matter and dark energy, 2 of the biggest mysteries in modern astronomy. Interestingly, Laniakea itself seems to be on the move. Astronomers have found that it's moving towards a region of space known as the Shapley concentration. This is another massive supercluster that might be part of a larger structure called the Shapley Supercluster complex. Now, after all this talk about the universe's structure, you might be wondering how we get all this knowledge. Well, much of what we know comes from some pretty impressive space observatories like the Hubble Space Telescope and the upcoming James Webb Space Telescope. First, let's chat about the Hubble Space Telescope. Hubble's been out there in space since 1990, taking amazing photos and gathering loads of data. The telescope can pick up visible light, ultraviolet light, and near-infrared light, making it a super versatile tool for astronomers. Hubble orbits about 547 kilometers above Earth, and its main mirror is a whopping 2.4 meters across. On top of that, the James Webb Space Telescope, JWST, could help us out with a bit of a puzzle we're currently facing in cosmology, which involves figuring out the size and expansion rate of the universe. This involves something called the Hubble constant, and right now we're getting conflicting results depending on how we measure it. So, JWST could help us iron out this discrepancy by offering us more precise measurements of the Hubble constant using different methods. One way it could do this is by observing standard candles. These are objects like certain types of stars, supernovae, or quasars whose true brightness we know. By looking at how bright they appear to us and comparing that to how bright they actually are, we can work out their distance. The beauty of using JWST for this is that it observes in infrared light, which isn't as badly affected by dust in space as visible light. JWST could also use gravitational lensing to help measure distances. This is when the light from far-off objects gets bent on its journey to us because it passes near a massive object like a galaxy. This can cause distortions and multiple images of the same distant object. JWST could use these distortions to calculate distances, which could help us get a better grip on the Hubble constant. Finally, JWST could also use cosmic chronometers to measure the universe's expansion. These are objects like old stars or galaxies whose ages we can determine by looking at their light. By comparing their redshift and their age, we can estimate the Hubble constant. Again, JWST's ability to observe in infrared is key here, as it provides more sensitive information about an object's age. So, in a nutshell, JWST could really help us to refine our understanding of the size and growth of the universe. And who knows? It might even give us a glimpse into the history of past cosmic cycles. Do you think the universe is infinite? Let us know your thoughts in the comments. Stay tuned for more mind-bending videos.